Hello and greetings. My name is Muhamad Shamsul Arif bin Arman, mention number 9980. Today I'm going to talk about our introduction. So, process scheduling is crucial for OS performance. The definition of process scheduling is responsible for selecting a processor process based on a scheduling method as well as removing a processor process. Next, we talk about round robin. Round robin is known for its fairness and flexibility. It also often outperform FCFS, SJN, and SRT in multitasking system. And lastly, for our study goals, which will be evaluating RR with varying time quantum and research for the metrics, turnaround time, waiting time, and the interruptions. And lastly, we'll be using Python to implement the method.
My name is Wan Fathan and I'm going to run the code with different time quantum. So before we start, there's certain requirement to run the code successfully. So first is we have to add the Python and the job list file in the same project. But as you see here, our job list file is in text file. Why is that? Because we use that and our program can read the text file and the job list beside from using the Excel file. So we choose to use that. And one note for sure to note for sure is that you cannot change the name, you cannot change what's inside it. If you change it, it will the code the our program will not recognize it and the program itself will fail. So don't change anything. So for the function itself, this one is to read the job list itself, read the CPU and IO cycles and the job list and everything. So this one, round robin, is to simulate round robin scheduling algorithm, which means it calculate everything, average turnaround time, average waiting time, and number of interruption based on the time quantum that we choose. So summarized result is just to show the result of the calculation. So without further ado, let me start this program. So enter time quantum. We can choose any time quantum, but for this project sake, I will choose 4 to show examples, which is 5, 10, 20, and 60. Okay, I will input this all first and will explain to you after that. So, different time quantum, yes please. 10, different, yep. Add another 20, y, and 60. Okay, so there's 4 examples here. I will explain one first. So, at the time quantum of 5, the performance metric, there's average turnaround time, waiting time, and number of interruption. And you can see the jobs detail here, the job list, and every job have its own turnaround time and waiting time here. So we do it in a nice table so that it's easier to see. And then you can see here the same thing for 10, just the value is different because different time quantum. But one thing to note for sure is that you can see here the number keep on decreasing for the turnaround time, waiting time, and number of interruption, as you can see here. So what we can see from our program is that uh, the more time quantum is, the decrease of turnaround time, waiting time, and number of interruptions are. So my friend will elaborate more on this. So yeah, so this is how our program run in different time quantum, as you can see here. And that's it from me, and I'll pass it to my friend next. Thank you.
Hello, my name is Muhamad Fikrul Amin, and here I'm going to explain on how our program gets the calculation results for turnaround time and waiting time. So first off, I'm going to explain for turnaround time. It represents how long it takes for a job to complete after it arrives. So a formula to get the turnaround time is basically completion time minus arrival time. As for waiting time, which is the time a job spends waiting in the queue or doing input output operation, is basically queue waiting time plus input output wait time. Right after we get the calculation results for turnaround time and waiting time, the calculated metrics are then stored into the metrics dictionary, where turnaround time is stored into metrics turnaround time and waiting time is stored as metrics waiting time. This allows the programs to easily summarize and display the results for each job. Next up, I'm going to explain how our program gets the calculation results for average turn time, average waiting time, and number of interrupts. So first, let's look at average turn time. To find their average, the program sums up all the turnaround times and divides by the total number of jobs. So it's basically sum of turnaround times divided by number of jobs. Next one, for average waiting time, to compute the average waiting time, we sum up all the waiting times and divide it by the total number of jobs. So sum of waiting time divided by number of jobs. And lastly, for number of interrupts. To explain what is number of interrupts, it is an interrupt occurs whenever the CPU switches from one job to another. In the code, every context switch increases the interrupt count by 1. Let's say if the context switches 25 happen during the simulation, the total number of interrupt is recorded as 25. This metric helps us to understand the overhead introduced by context switching.
Hello, my name is Abdul Fiedry Ashraff, and today I'm going to present about the comparison chart and comparison table. Okay, first I'm going to talk about the comparison table. As you can see, as the time quantum increases from 5, 10, 15, 20, the average turnaround times is decreasing. Also, the average waiting time is decreasing too, except for the time quantum at 40, where it's increasing, then decreasing. For number of interrupts, it is also decreasing. Next, the comparison chart. This is the comparison charts for average turnaround time, average waiting time, and number of interrupts. As you can see, for the average turnaround time, the chart is decreasing. For average waiting time, the chart is also decreasing, except for time quantum at 45, where there's a little bit of increasing, then back to decreasing. And for number of interrupts, where all the chart is decreasing. Thank you.
Hi, my name is Shamrin, and I would explain the evaluate result parts. So, for the shorter time quantum, which is 5, 10, 15, and 20, the issues arise here is high average turnaround and waiting times, where frequent context switching occurred in here. When the time quantum is decreasing, the overhead of context switching will be increasing. This would be negatively impacts on the performance for the entire system. Okay, now I would explain for the larger time quantum. We have larger time quantum for 45, 50, 55, and 60. The benefits we got in here is lower average turnaround and waiting times, where fewer interrupts occurred in here. This means fewer context switches happen. It would help the system run more efficiently. So, lastly, for the conclusion for larger time quantum, it improved performance but may delay or slower in responsiveness. Thank you. That's all from me.
Good morning everyone, my name is Junior. Today I will be discussing our recommendation to use a time quantum of 50 for the round-robin scheduling algorithm and the reason behind it. The time quantum of 50 strikes the perfect balance for optimizing system performance while maintaining efficiency. Let me explain why. A quantum of 50 minimizes waiting time, turnaround time, and interrupt. This ensures the processes are handled fairly without significant delays. This value reduces excessive context switching, which keeps the system efficient and avoid wasting resources on the frequent task swap. It achieves high CPU utilization and throughput, ensuring the system runs smoothly while minimizing delays and interruption. Finally, this quantum ensures the system handles the workload effectively, maintaining both responsiveness and efficiency, crucial for real-world application.
For the conclusion, the round-robin RR scheduling algorithm is effective for fair CPU time allocation. For the first one, time quantum analysis, the smaller time quantum increase context switching, which will reducing performance, while the large time quantum reduce context switching but cause delays in responsiveness. Another one, optimal time quantum, a time quantum of 50 is an ideal one, which will minimize waiting and turnaround time, thus ensuring high CPU utilization and true output. This will achieve system efficiency and effectiveness for the given workload.